I will start with some very elementary things to introduce what you may probably not know, maybe not all of you, the spinor tenfold. So I start with a baby toy model of the spinor tenfold, which is just the usual Grassmannian G25. So I use the notation for the Grassmannian of two-dimensional vector subspaces of a five-dimensional vector space V5. And let's say over the complex numbers, but we'll see. So there is the usual Plucker embedding in P9. And so the Grassmannian has, let's call it G. The dimension is 6, and the canonical bundle is the restriction of O minus 5. So this is a Fano sixfold of high index. And we know that this is nice. This is usually a nice property of homogeneous spaces like this, that there are Fano of high index. So if you're interested in Fano manifolds, it's a good way to construct Fano manifolds of lower dimension by cutting with hyperplanes. And if you don't go to too low dimension, you still get the Fano property. Okay, so here you can try to cut up to codimension 4 to remain Fano. So okay, so you have codimension 1, 2, 3, 4, let's say, and you hope to get many Fanos by this process. So you see, there is this interesting property here that in codimension 4, you will get a surface which is Fano of degree 5, because the Grassmannian is degree 5. So you get a del pezzo of degree 5. And you know that there is a unique such surface if it's smooth. Okay, so maybe contrary to your expectation, you get a unique del pezzo surface. And the same property is true for the other cases. You get a unique Fano threefold, a del pezzo quintic threefold. And this is again true in codimension 1 and 2. So let me switch to the yes. So things are slightly more interesting in codimension 5. So in codimension 5, you will get curves with trivial canonical bundles, so elliptic curves. So over the complex numbers, this is not so interesting, but oops. So codimension 4, codimension 5, you get elliptic quintics. So for the complex numbers, not so much to say about those, but this was studied by over the field of rational numbers, over number fields, and there is a rich story, which is part of the study by Bhargava and his co-authors. So they realized that there is a series of representations like wedge 2 V5, from which you can construct interesting families of elliptic curves. And you can use the group actions, the Lie group action on your representation, to parameterize the isomorphism classes of the elliptic curves you get of a cube. So this was a very powerful tool that Bhargava used to get his famous results on the statistics of arithmetics of elliptic curves. So I should mention Bhargava and his collaborators, Wei Ho, Jack Thorne. So they studied around 2010. So this led to what is sometimes called arithmetic invariant theory. Okay. And so what people also realized at the time was that there are some cases, some representations, some special ones, which have a nice connection with curves of a higher genus. And there was a nice paper in 2012 by Gruson, Sam, and Wyman, where they studied that a little bit. And then we realized that it's only part of the geometry of this representation is extremely rich. So I started a project 10 years ago, actually in Marseille, with Tanturi, Benedetti, Filippini, then Faenzi, Bolognesi. So this is still in progress, actually. And what I'm going to tell you about is a little piece of this program. So we will see one representation and look at the geometry, which is quite interesting from my point of view. You will see from the many reasons which make this geometry interesting. So So the spinor tenfold, what is that? So you start with essentially the same Plucker Grace-Minion. So this time this will be, you start with a 10-dimensional vector space, and you look at the Grace-Minion G510. So it's the Plucker embedding. And now you add a little ingredient, which is you consider a non-degenerate quadratic form on your space V10. And so inside the Grace-Minion, you have the orthogonal Grace-Minion, which parameterizes those 5-dimensional subspaces which are completely isotropic with respect to the quadratic form. Okay, and so if you already met this, you know that there are actually two connected components. And this is the And moreover, when you restrict the Plucker line bundle to each of these components, there is a square root. Okay, so there is a minimal. This square root defines the minimal equivariant embedding, and this is inside what is called a half-spin representation of spin 10. So this half-spin representation, so there are two of them, hosting the two connected components. So they are indistinguishable. They are both of dimension 16. So the projectivization is P15. And since you have taken a square root, you get back to your usual embedding by a quadratic Veronese. Okay, so this is the spinor tenfold. So I can take S plus or S minus. As I said, they are indistinguishable. They are isomorphic as embedded projective varieties. So the dimension is 10, as you guessed, and the canonical bundle is O minus 8. So you will get interesting Fano manifolds by cutting with hyperplanes, and you have a lot of freedom because the index is high. You can cut up to codimension 7 and get interesting objects. So let's see. So we can cut bilinear spaces. So codimension 1 to codimension 7. So actually, so codimensions that's in 7, 8, and 9. So these cases are, so 7 is the last case for which you get Fano, so you get Fano freefolds. Homogeneous 7. Then you can still get something interesting. You get K-free surfaces. Homogeneous 7. And codimension 1, you get canonical curves. Again, homogeneous 7. So this case where this is part of the work of Mukai, who gave this kind of models for, so Mukai proved that any Fano freefold, prime Fano freefold of genus 7 is a linear section of the spinor tenfold. And the same for generic K-free surfaces and canonical curves. So if you know the classification of Fano freefolds, you already met this spinor tenfold, and you know the important role it plays. So what I want to discuss today is more the other extreme. So what's going on in low codimension. So and we will see that something similar to what happened for the Grassmannian is also true here. We will have uniqueness in codimension 1. And then something interesting in codimension 1, 2, and 3. And then there is the most interesting case is a family of sixfold that you get here. Okay, so this is the general setting. Any questions so far? Okay. So another common feature of my two varieties is their equations. So for the Grassmannian, you know the Plücker equations. So if you have an element in wedge 2v5, how do you decide if it comes from the Grassmannian, if it has rank 2? So it has rank 2, so if and only if you just compute the wedge product of omega with itself and you ask this to be 0. Okay, so this formula defines a map from let's say S2 wedge 2v5 to so that's a 4 form, which is the dual space. Okay, so you have in other words, the Grassmannian is just cut out by these 5 quadratic equations parameterized by V5 dual. Okay, so which you can see as a quadratic map. The projectivized version would be a quadratic map like this. So for the spinor tenfold, that's completely similar. So the fact is that there is a similar map from S2 delta plus to V10, which gives you the
so what does this map between projective spaces do?
This is the same. You take take omega, you map it to omega wedge omega.
I mean,
This is the map I wrote here.
yeah, this I understand, but you promised us equations, so I thought you would show us a vector bundle over the projective space.
The equations are here.
Okay.
So this is 0 in this space. So the equations are parametrized by this space, which is V5 dual. Okay, so this means that this rational map is defined outside the Grace-Minion, which is the zero locus of these equations.
Okay.
So you have a similar description of the equations of the spinor, tenfold. It has 10 quadratic equations given by such a map. And so you have a similar map, little gamma. It takes you to P9, which is defined outside the spinor tenfold. And remember, there is a quartic on V10, so geometrically in this P9 there is a quartic hypersurface, and gamma actually has its image in this quartic. So there are lots of similarities between these two varieties, but let's stick on those. So now let's discuss the low codimension sections. Oops. So in codimension 1, so I'm interested in smooth section. So in dimension 1, I need to avoid the projective dual of the spinor. And in fact, it turns out that the projective dual, that's a highly degenerate case. The projective dual is the other spinor tenfold. The two spinor representations are dual one to the other. Okay, so any hyperplane defined by a point which is not in the spinor, in the negative spinor tenfold, will define a smooth sections. And the other fact is that this complement, the complement of S minus, is acted on transitively by the spin group. There is only one orbit. So this means that up to projective transformation, there is only one smooth codimension 1 section. Okay, then I will use some the notation, the following notation. Maybe I will use XL to be S plus intersected by some linear space P of L. So I will use the following notation. I will be a subspace of delta minus, which is the dual. And so I cut with the orthogonal. So the codimension is the dimension of L. So if I go to codimension 2, what are the possibilities? So I have this this P of L now, which is a P1. And I can use the map gamma. So I took it for delta plus, but there is the same one for delta minus. It's called delta minus. Takes me in Q8. So this is a quadratic map. So I get a conic inside the quadric. And you know there are two types of conics in a quadric. Either there are two conditions. There are two possibilities. If you look at the linear span of this conic, it can either be contained in the quadric or not. Okay, so there are two possibilities. So for this, we found there are two types. That's a bit uncommon. There are two types of up to projectivity of codimension 2 section, the general one and the special ones. So you can degenerate the general one to the special one, which is still smooth, with the same topology, etc. So codimension 3. What is natural is to look at, so if you have your XL, so you can look at the oversections. Okay, so you look at the codimension 2 sections, xk. So they are parameterized by so hyperplanes in L. So this is just a P2. And you can wonder what are the special ones among the oversections of XL. What are the special ones? What are they parameterized by? And the fact is that special oversections are parameterized by a conic. So I forgot to say something important, which is that being special in codimension 2 is a codimension 1 condition. So this defines a hypersurface in the Grassmannian of two-dimensional spaces in delta. Maybe I should write it here. So they define so inside the Grassmannian of them two planes in delta minus, I have a divisor, a hypersurface. And this was studied by Kuznetsov. There was a nice paper by Kuznetsov in 2018 where he studies this divisor. He shows this is a quadratic divisor, so an intersection of the Grassmannian with a quartic. And we call that the spinor quadratic complex. So now when you go to codimension 3, the situation is a bit richer. So as I said, you get a conic parameterizing special oversections. So obviously for a conic you have several possibilities. So to be precise, I should say that this is a quadratic condition on the plane. So special oversections parameterized by, so in general this will be a smooth conic. Then you can have a singular reduced conic and a double line. And the last possibility is that all oversections are special. Okay, so this is the case where these are called very special codimension 3 sections. So you have the fact is that you have only these 4 possibilities up to the action of the spin group, up to projectivity. You have exactly 4 cases, so generic 1, 2 intermediate situations, and then the very special ones, which are characterized in different ways. And you see that again you have a codimension 1 accident, which is the singularity of the quartic. So this defines again a divisor inside now the Grassmannian G3 delta minus. Okay, and what when you can show. So I realize I forgot to say that this is joint work with Yin-Chil Yu. So R3 is a quartic divisor. Can even give the explicit equation. And it has a very nice property, which is the following. If you suppose you take, let's say, M inside delta minus, general, of dimension 4. And you cut out your divisor by the Grassmannian of 3 planes which are contained in M. Okay, so this is just M is dimension 4, so this is the dual projective space. So this is actually a copy of P3. And the nice fact is that this is a Kummer surface. So this divisor has this very special property to give you Kummer surfaces when you mod out by when you intersect with this covering family of P3s. So maybe I should tell you a little about Kummer surfaces to explain why this is true. So that this is a very classical object in the So let me briefly remind you a few properties. So they are quartic. So this is a quartic surface, which is a singular, which is nodal, with the maximal number of nodes, which is 16. Okay, and so you have so this was studied a long time ago, and one of the nice properties is that this is projectively self-dual. So if you take the family of tangent hyperplanes, you get a Kummer surface, actually the same Kummer surface. And so this means that since this the dual has 16 singularities, this means there are 16 special planes in P3, which cut out your Kummer surface along double conics, actually. Okay, so there is a dual, so there are 16 singular points, and there are 16 conics, and they form a special configuration. So that's completely symmetric, so through any singular point you have 6 of these conics. So you get what is called a 16-6 configuration. And well, this is a nice combinatorial object. So the automorphism group of this configuration is a big. The rather big group is the order is 11,520. So there will be a lot to say about that, but the relationship with what I've been saying is provided by a nice construction due to Felix Klein. Which is like that. You start with a quadratic line complex. Quadratic line complex in the classical terminology means a quadratic section of G24. G24 is itself a quadric. But you see it really as a Grassmannian, and you cut it by a quartic. Okay? And so when you do that, you can observe that if you take, so maybe I should call it V4 to be more consistent. If you take H in V4, so this is a hyperplane, then you have the two-dimensional subspace contained in H. Again, that's a P2. So when you cut it with Q, you get a conic. So this will construct a conic bundle over the space of hyperplanes. Okay, so over the space of hyperplanes, P3 dual, you have a, maybe I will call it GQ, a conic bundle. And this is a usual way to construct nodal surfaces. When you have a conic bundle like this, it will, in general, if it's well behaved, so the geometric fiber is smooth, then in codimension 1, you get singular conics. So this defines a surface. And you get some, in codimension 3, you get double lines, which will give you some singularities of the surface. And so Klein's observation is that you exactly get a Kummer surface and its 16 singular points by looking at a general quadratic line complex. And of course, there is a symmetric picture. If you take a line in V4, then you can look at the two-dimensional spaces containing this line. This is again a P2, so you have the same construction over a PV4. And this time you get K and it's 16 singular points. Okay. So if you implement this Klein's construction in the setting of the spinor quadratic complex by restriction, you get exactly this property. Well, by the way, I can say a little more, maybe. As I said, there is a relationship with curves of genus higher than 1. In fact, genus 2, because these Kummer surfaces, as is well known, are a quotient of abelian surfaces by plus or minus 1. And you can see that like this. If you look at Q, so that's the slight abuse of notation. This is an element of the linear system on the Grassmannian 2. But you can see that this is the same as the space of sections over you look at the flag manifold. You take flag manifold of lines and hyperplanes in V4. Okay, so this is and now you take the vector bundle U1 dual square, tensor sim2 U3 U1 square. And once you have observed this, you see that this section of this bundle over the flag manifold, it defines two objects. You can see it as a family of quadratic forms, binary quadratic forms. So there are two accidents. It can degenerate, it can become 0. Okay, so it degenerates along F, which is a quadratic section of the flag manifold. And it is 0 along a surface. So the flag is dimension 5, you get a surface. And so you get so the flag has the two projection over projective space and its dual. And so, as you already guessed, the images are exactly the Kummer and its dual. So you can check that here is an abelian surface. The two projections are 2 to 1. And the nice fact is that F is the unique quartic section which is singular along A. So if you know about cobble hypersurfaces, this is exactly the kind of phenomenon that are observed for cobble surfaces. They have a very special singular locus, and they are uniquely characterized by this property. Okay. Any question? So if no, there will be a new player now. When I go to codimension 4, the surprise for me was that this is related to some nice unexpected object, which is the exceptional Lie algebra. E8. So we have already met E6 yesterday in Sasha's talk and E8 in Ilya's talk. So you may be a bit familiar with the root systems of types E6, E7, 11, but maybe not with the Lie algebra. So it's if you know about spin representation, it's rather easy to construct E8. You can start with SO16 and add one of its half-spin representation. And the claim is there is a way to construct a Lie bracket on this, which gives you E8. Just from the Lie bracket here and the action here. So if you don't like spin representation, you can even start from SL9. And you add wedge 3 C9 and wedge 6. And the claim is that this is E8. There is a natural way to construct a Lie bracket on this sum, which gives you E8. Okay, and when I say nice, in particular, these are grading. This is graded over Z2. This is graded over Z3. And another similar decomposition related to what we're studying is the following one. You start with SL4 times SO10, and then C4 tensor delta plus, wedge 2 C4 tensor V10, and C4 dual tensor delta minus. So I claim this is, again, there's a natural bracket you can construct on this sum, which gives you E8, and it's graded over Z4. So why is that nice? Well, first thing is that you see here what is homomorphisms of C4 to delta minus. So if we take an element here, obviously if it's injective, the image will be a point in the Grace-Minion, so it will define codimension 4 section of the spinor. Okay. And then the observation is that, well, this is what is called a theta representation. So there is a very nice theory due to Weinberg and many other, mainly Russian mathematicians, where they studied this kind of representations which appear in ZM gradings of simple Lie algebras. And they prove they have very nice properties, essentially. So if you have a simple Lie algebra, semi-simple Lie algebra, there is this Jordan theory, which gives you a classification of orbits, which is similar to the usual Jordan theory of matrices. And they prove that this extends to this kind of representations. Okay, so the basic ingredient are you have the semi-simple elements, which are parameterized by some in the usual setting by diagonal matrices. Then you have the nilpotent one, and then you have the mixed cases. Okay, when the semi-simple element is not regular, so there you have some eigenvalues that coincide, you have some possibilities for the nilpotent part, finitely many. So this kind of classification still exists for these theta representations. So this means you get a huge amount of information from this Jordan-Weinberg theory. You can essentially classify all the orbits of inside this theta representation and therefore all the orbits of codimension 4 sections. Okay, so we have a family of Fano manifolds of dimension 6, and we know essentially everything about those. So the actual, so in theory we know everything, but the actual classification is not so easy. It's quite a piece of work actually. So we needed an expert to help us, and it was done by Willem de Graaf, who was a collaborator of Weinberg. And for example, he found 144 nilpotent orbits. So you need good computer programs and good skills in this theory to be able to get this. So if you are interested in a smooth section of the spinor, the nilpotent orbits still play some role, but this simplifies a lot the picture, because only 3 of these 144 nilpotent orbits give smooth sections. But still they are there, and we can study them more or less explicitly. So time is flying, so what can I tell you then? For example, we can give a list of possible connected automorphism groups. The list is like this, so you have, of course, the trivial one, multiplicative group, additive group, 2 copies, then you can have 1 copy of GM and 2 copies of the additive group, and then you can have SL2, GL2, SL2 times SL2. Oops. So this is the complete list. And maybe just a statement to be a little more precise. So we can say the generic automorphism group is actually Z2 to the 4, the finite group of order 16. And the other extreme is this case. There is a unique section with automorphism group of type SL2 times SL2. And of course, you observe that this has dimension 6, which is also the dimension of the variety. So you can wonder what is the generic stabilizer, and we found that's a finite group. So it's a compactification of SL2 times SL2 modulo mu 10, 10th root of unity. So if you know the classification of Fano freefolds, it's a bit similar to the Mukai-Umemura example. You have a family and a unique member, which is a compactification of SL2 modulo finite group. So this is one. So this is the kind of thing you can say. So briefly, let me say a bit more about the semi-simple objects. So in the usual setting, they are parameterized by the space of diagonal matrices, so a Cartan subalgebra. So in this generalized theory, this is called a Cartan subspace. So the Cartan subspace here, so Wienberg tells us that this has dimension 4. So when we projectivize, there will be a three-dimensional family of sections. So I don't have time to speak. There's nice combinatorics going on here, but let's forget this. Let me just say that, so it's like in the usual theory. You have a semi-simple matrix is determined by its eigenvalues. So you have the diagonal, you put it in diagonal form, but you have the choice of the order given by the symmetric group. There is the ambiguity of the order of the eigenvalues. So there is a finite val group acting here. So there is a similar thing, which is called a little val group, which has dimension, which is a complex reflection group. Of order 46,080. Okay. So this means you have complex reflection groups. It means that the group is generated by reflections along hyperplanes. So you have an arrangement of 60 reflection hyperplanes. Okay, so I will not draw the arrangement, but you have something like this. So you have when you have an arrangement of hyperplanes like this, you can distinguish some linear subspaces by the number of hyperplanes they are contained in. Okay, so typically you have special lines, special points. So these are called the flats usually. So in this case, you have three types of so one type of hyperplanes, three types of special lines, three types of special points. Okay. So in particular, very briefly, so first thing you can ask is what is the discriminant? So you expect the discriminant to be a hypersurface. It's a priori a codimension 1 condition, so you expect the union of the hyperplanes. It's not the case. Discriminant, because of these special properties of the spinor, this discriminant has codimension 2. So it's the union of 30 special lines. So when I cut it with this set of semi-simple elements, okay, so it means that so I miss some special points, and in particular this so discriminant will be like this, a union of lines, and you miss some points, and among those special points you have this SL2 times SL2 variety. In fact, what the hyperplanes correspond to is also a kind of discriminant, but it corresponds to the quadratic complex I defined for you. Okay, when I take an element in P of C, I get a spinor, a section of the spinors. I have this quadratic complex, and the quadratic complex is singular exactly if I am on one of those hyperplanes. So actually, the quadratic complex when I restrict it to P of C, gives me a map, a rational map, to a subspace of the linear system of the Grassmannian, of quadric section of the Grassmannian, and this is actually P4. Theta 5 has dimension 5. This is a special representation of the little Weil group. And I have the same phenomenon for the Kummer. If I can associate to any element of C a Kummer surface, I get another representation. So I can take 2 minutes to give you the statements we have. So the image, these are quite interesting objects actually, but very classical. So the image of should have given names. So the fact is that the image of Q, so this is inside P4, is what is called the Iguza quartic. Sometimes Castelnuovo-Richmond, quartic. So this is a special quartic hypersurface which is singular along 15 lines, which has a symmetry. For symmetry, the symmetry group in 6 letters, and this is the unique such quartic. And the image of K, also in P4, is the Segre cubic. Okay, which is actually the projective dual of the Iguza quartic. Okay, so very naturally, from this construction, we recovered these very classical objects. And in the end, if I can summarize the result, is that the GIT moduli space, so of spinor codimension 4 section of the spinor, which would be this GIT quotient. So this is the same as what I get from C4 times delta plus. Well, there is a Chevalet theorem which tells us that this is the same as the quotient of P3, the projectivization of C by this complex reflection group. So by Chevrolet theorem, this is a weighted projective space of exponent 2, 3, 5, 6. And this is isomorphic to the moduli space of Kummer surfaces. So this is very similar to the kind of statement that Bargava obtained for elliptic curves. You get some quotients of representations which are identified to moduli space of elliptic curves with some additional data. And here we get essentially genus 2 curves plus some additional data. So I stop here.